Okay, Year 11s, welcome to the latest edition of Mr. K going through essentials questions, topic 4, question 37. So, a 7.0 gram sample of cesium is sealed in a glass vial and lowered into 250 milliliters of water at 90.00 degrees Celsius. When the cesium had melted, the temperature of the water had dropped to 88.98 degrees Celsius. Determine the molar enthalpy of cesium, for cesium. So, what we're looking for is, where are we? We first have to look at the water. So that's what we have the information about its temperature. So Q is, actually, and we also don't know the starting temperature of cesium. So we're going to look at Q. We have, that's for the water absorbed by the energy absorbed by the water. The energy lost by the water because its temperature has decreased. So Q is equal to M times C times delta T, which in this case it's 250 milliliters of water, so 250.0 grams of water times 4.18 joules per gram per degree C times by our delta T, which is 1.02 degrees Celsius. So that's the difference between 90 and 88.98. Cool. So that is our number, and we're going to throw that into the calculator. So I'll just put that in there now. 250 times 4.18 times 1.02 is, that's just to be clear, that should be a negative temperature because a negative change because it's decreased. So it's very easy to make these mistakes, by the way. So we have negative 1065.9 joules, and in the correct number of significant figures, because it needs to be 3, because this and this have 3 significant figures, that is negative 107 joules. Sorry, 1070 joules. That's got 3 significant figures. Now that's the amount of energy that has been lost by our by our water. Now what we need to do is it's wanting the molar enthalpy for cesium. So the question isn't actually very clear here because it's not actually telling us. Well, it's a bit unclear as to what it actually wants. So I'm going to assume it's information that I can readily get. So if this is, so the molar enthalpy for cesium, either way, let's have a look. This would be an equation that we might be able to use. Oops. So number of moles times C times delta T. I guess the tricky thing is we don't really know what this delta T is, and we don't know what C is either. We can work out N, but the fact that there are 2 things missing here means that this is probably not what we're looking for. So in that case, I think what we're looking for is our delta H is equal to our Q divided by our N. In which case, N is equal to mass over molar mass, which is 7.0 grams divided by the molar mass of cesium, which is CS, and that is 132.91 grams per mole. And that is equal to, so that's 7 divided by 132.91, which is 0.0527. But we have two significant figures, so 0.53. So our final answer would be negative 1065.9 joules divided by 0.052667. Now, you can tell that these numbers are not the exact same numbers I wrote down for the answers before. That is because when you go to put your answers into calculations, you should not be using the answers that you've corrected the correct number of significant figures, it's best to put in essentially the whole number from the calculator that comes out. And that will give us, our final answer will be 1065.9 divided by 0.052667, which gives us a delta H. So this is energy that's been absorbed by cesium to make this happen. That would be positive 20,238 joules per mole, which we can correct to 20.238 kilojoules per mole. And lastly, to correct to the right number of significant figures, because in this equation, our this is a bit tricky. So our Q and N have lots of numbers there, but the number that our N and stuff were only known to two significant figures for our grams. So we're going to still be limited by our accuracy for our accuracy for our mass. So we're going to have two significant figures, which gives us positive 20 kilojoules per mole. So hopefully that is what they're actually asking for. But again, they're not very clear, and this is the only quantity that we can work out, because this here, if we're looking for the molar enthalpy, so the molar heat capacity, that wouldn't work. So we are looking for this one here, the molar heat enthalpy for cesium to melt. So that's the bit that they're not clear about. If they said the enthalpy of liquefying or melting, then that would work. Either way, so moving on. We have 8.0 grams of ammonium nitrate is dissolved in 1.0 liters of water, and the water decreases in temperature from 21.0 to 20.39. Determine the molar heat of solution. Now, we need to look at the water first. So the amount of energy, so the whole point of these, whenever you're doing it in water and measuring the temperature, is we can find the Q value pretty easily because we know the values for water. So Q is, again, M times C times delta T, which is the mass of water, which is 1,000 grams in 1 litre, times 4.18 joules per gram per degree C, times by our change in temperature, which in this case is 0.61 degrees C. And it's a decrease, so it has to be negative, because the water is losing this energy. So it's giving it to the ammonium nitrate water system. Okay, that gives us, where are we? We got 1,000 times 4.18 times 0.61, negative 0.61, gives us negative 2,549.8 joules. Again, because grams per gram per Celsius cancel each other out. And in this case, just to clarify, we're given the mass, we're given the volume of water in 1.0 liters, which will mean even though we're going to use 1,000 grams, we don't actually know how accurate that is. So we're going to limit our final answer to two significant figures. So I'm going to leave this here because I'm going to keep using it, but our final answer, we need to remember, is two significant figures. So that's the energy that has been taken away from the water, which means the amount of Q being absorbed by the dissolution is the negative of that. So the opposite of that, which is positive 2,549.8 joules. So that's the energy that's being absorbed by our reaction. And we know our delta H is our Q of our reaction. Actually, I should probably put reaction, that's a bit more general. Q of the reaction, the Q of our reaction over the N, and N is equal to 8.0 grams divided by the molar mass of ammonium, actually nitrate, NO3. So I'll find that out. So the molar mass of ammonium nitrate is 80.043 grams per mole. So I looked it up, but you need to be able to work it out from this formula. You're not expected to know what ammonium nitrate is, but this is a textbook question, which means you're allowed to look things up. And that there will be equal to 8 divided by 80.043, which, it's going to be pretty close to a tenth, so 1%. So we have 0.10. That's close enough because it actually is 0.0999. So rounding to 0.10 moles. Now, that means our Q of reaction is positive 2549.8 joules divided by 0.10 moles, which is the same as times by 10. So that's going to be positive 25,498 joules per mole, which is 25.498 kilojoules per mole, which is two significant figures. It's almost 26, but it's going to be 25, positive 25 kilojoules per mole. Now we can only have two significant figures because our mass is only in two significant figures. Cool. Hopefully that helps. I'm not sure how long we're up to, so I'm going to I'll check to see how long it's been. We've got about 2 minutes left, so I'm going to stop this one as well.